All right. Thank you so much for the invite, for letting us present our work here today. I'll be talking about Ego Adapt, where we basically attempt to combine distillation and policy learning for several egocentric tasks. We'll talk about them in a while. We have the poster presentation on October 22nd during poster session 3. Please feel free to be there. We'll be happy to talk more. I'm Sanjoy. This work is basically a collaboration between University of Maryland, Meta, Reality Labs, WPI, and University of Toronto. Yeah. So first of all, what is the motivation? We know that we have seen remarkable progress in the egocentric space over the last few years, powered by many excellent data sets, a lot of challenging tasks, and then a lot of efforts both in the modeling as well as in the data curation front. But in most cases, the problems that we observe in these sort of models are we have to operate in a limited compute budget, and in most cases, we also have to make sure that the models that we have whichever problem we are trying to solve, these are real time because these are in most cases set up in wearable devices or into gadgets which the person is wearing and then sort of moving around with not access to power, compute, or at least even if we have, it's very less. So that those are some of the practical challenges that we have to keep in mind. But at the same time, keeping efficiencies in mind, we cannot also do away with the performance because performance is also important. So we have to make sure that no matter how much we are focusing on the efficiency, we are still able to achieve some decent performance. So even if we take a look at say the Ego 4D baselines, even the 3D CNN based models, they operate at more than 100 Gmax per second. So which are sort of infeasible for most of the tasks that we are interested in general. So what are the key questions that we are trying to ask in this work? So we are trying to understand that whether all the modalities, so by modalities, I mean it can be vision, it can be audio, it can be like gaze again is a part of visual information, it can be I don't know, like head movement, eye move, all these different modalities we are dealing with. Does all of them play some key role in solving the downstream tasks that we have in hand? Or do we still need only maybe a subset of them? And it's up to us as to how do we combine or leverage these tasks, these modalities to solve some of the certain tasks. So that's one. The second question that we ask is, uh, which one to use and what is the smartest way to switch between some of these modalities to make sure that we are not compromising on the performance, but we are also working at a fairly fast and efficient space in order to tackle the task we have in our hands. So what is the broad question that we try to ask? The question that we are asking is, can we somehow combine the policy learning and the model distillation together to make sure that we are tackling some of the challenges in this space? So the first component, so the training we design is in multiple stages, in 3-stage training. But the first step of that is just getting a very tiny distillation module running. So for the distillation module, what we do is we have primarily 3 objective functions that we are trying to optimize: the KL divergence, the L1, and of course the in the logic space, we are trying to optimize the GT loss. So what we are trying to do, why these are important essentially. The KL divergence is important because we are taking a huge teacher model and then we are trying to ingest all the knowledge into a small student space. So it requires the soft targets to be aligned in the semantic space. So just to give the model an overview of what the task is about and what sort of the overall notion of the tasks that we have in hand. For L1, we basically try to align the intermediate representation in the feature space across, because we are doing a cross-modal distillation. We have multiple modalities. How can we make sure that they are somehow aligned in order to solve the broader problem in hand? And also in the logic space, we need to have overall comparison with the GT so that the model that we are trying to distill, it is somewhat conversant of the work that we are trying to solve. So this is the distillation module. Once that is done, what we have is the policy module. It looks a bit complicated at the beginning, but it's fairly simple in a way that the overall aim, we are trying to gather models which are relatively smaller and cheap. So if we see the components that we are using, those are very fundamental and in most cases fairly primitive kind of model. So we are using RCNN to make sure that, because we are operating at a time series data, so it's operating over a period of time, like on the videos or maybe the IMU head motion, all of them are have a temporal component. So we are somehow making sure that these are ingesting all this different information, but also making sure these are capturing only the crucial bits and pieces, and we can remove the redundancy as much as possible. So what we do, we unify the continuous space in the distillation and also in the discrete space, the policy learning, by making sure that these are differentiable, because as we can understand, the action space that we have, that is discrete, and we have to somehow use maybe something like a Gumbel softmax, which will essentially help us make this thing differentiable and also smooth, so that we can sample over this discrete space and also do the back propagation for training such a model. Now in the stage one, what we have, as I was referring to earlier, so we stabilize the knowledge translation. We have this heavy teacher network. We do a cross-modal distillation into a smaller student model by optimizing all these three different objective functions, and essentially only the student network is trained in this case. In stage two, we freeze the policy network and we only train the student network. We freeze the student network and we only learn the policy module. Why? Because in the first stage, we have a student model which has somewhat understanding of the overall task, but now the overall attempt is to make it work with a policy module. They should somehow understand what sort of instruction it will provide, and then how the student model need to intake all this information. So for that, the policy network is being trained in the stage two. In stage three, where we essentially have both the models, the student model is also aware of the kind of tasks that it needs to solve, and then there is a policy module which has been trained somewhat. So essentially, now it's time for both of them to be trained together. So that's the overall objective we are trying to take care in stage three. So after this multi-stage training that is involved, combining all these things together, we finally obtain the overall module. Now let's look at some of the results in the egocentric action recognition results. So let's take a look at maybe the Epic Kitchen's 100 examples. So as we know, there are many such examples in this space. Audio is. So what we have is there's a person who is doing the chores. He's cleaning, washing the plates, sometimes opening the tap, faucet, and then cleaning, and then doing around different things. So what is the idea? So the idea is can we use audio as the previewing mechanism? Can we use just the audio to understand what all distinct events are there? So once we have identified that, then the visual processing becomes easier, because we do not need to sample densely across all the different frames or the entire clip. We can only sample maybe part of the entire visual clip, or maybe just one frame for a given audio event of interest. So in the chores, open the tap, and then washing the dishes, and then cleaning the counter. These are the three primary events that we have seen. If I just play the audio, it's just essentially what we saw in the previous video. So if this is the audio stream, now after the audio preview has taken place, the idea is to make sure that we are only understanding. So at the second around, there is potentially a distinct audio event, which is opening the tap maybe, and similarly in the 14 second and 28 seconds. So these are the three distinct events. Those are happening, and by audio previewing, mostly these tasks can be solved with a very high confidence. Now, once that has been done, what do we need to do? We just need to, for the action, for the exact event, what is happening, we just need to understand, maybe just pick a representative frame within this epsilon ballpark. So if we have identified a certain area, we can just pick maybe one frame which is representative for that specific task. Similarly for the task 2 and for the action 2 and the action 3. So on and so forth. So we obtain the most salient K-frames, which are the representative of the individual actions those are being performed. So the selected frame that is fed to the student model, which is basically the distilled student model, which can do the action recognition. And then essentially, once we pass this, the overall response is place the cup in the sink, which is the first action that we see. In the second event, what we see during the 14 second, there is a student model. The same student model is taking this representative frame, and it is suggesting that, okay, there is a possibility that the person is starting the tap right now. Similarly, for the other event, there is like washing the towels, which is again a potential third action event that we are interested in. Now, for active speaker localization, we see so if we start it from the beginning, so this is what is happening. So this the left one is without the policy module, so we call it temple. So without the temple module, you see there are a lot of miss like detections in the active speaker space. If we take a close look, so the blue ones are the non-active speaker, and the red ones with solid outline is the active speaker, and the other one is the model prediction. We see in most cases it's doing a lot of mistakes, but when we actually incorporate the policy module, it's doing much. The rate of error has reduced a lot. So that's definitely an indication that combining the policy and the distillation is helping. Now, quickly talking about some quantitative results. So we have three different tasks. One of them is the action recognition, the other one is active speaker localization, and the other one is behavior anticipation on the AEA dataset. What we see is we operate at different, based on the different input format that different model follows. We operate at different input resolution, and then we try to predict the verb, noun, and also the action, because in order to predict the action, we need both verb as well as noun. And we also report the Gmax of most of the models just to compare where we stand in terms of the performance as well as efficiency. We see our model EgoAdapt, by the way, TIM is the teacher model from which we do the distillation. So we see, although there is like very delta drop from the teacher model's performance, but the Gmax that we are gaining, that is significantly almost like if not nearly 4 times the Gmax, which is considerable when it comes to some of these edge devices that we are talking about. Similarly, for the active speaker localization task on the EasyCom dataset, there are similar performance gains, especially in terms of the energy consumption and also the number of parameters that we see. It operates at almost like 7 times less for the parameters, and energy also is significantly lower compared to what the teacher model is operating at, and the performance is almost same, if not comparable. So and then similarly for the behavior anticipation task, we are trying to predict gaze, orientation, trajectory, and also report the overall energy consumption across all these tasks, which is averaged over the clip level that we are doing, and then we are aggregating over the entire video. So that is how the overall performance is. Quickly talking about the ablation results, we see that here in the selected frames, if we pass on the audio, we follow the similar strategy like audio previewing, and these are the ground truth actions, and the frames, those are represented. Basically, these represent from this frame to this frame, this certain action event is being performed. So if we look at up till audio stage 2, there are few loose coupling, as we say, because there are certain mistakes that we are doing. For example, in this, it's saying that put cup down. It has started, it has detected a task which has not started yet. So it's probably due to the fact that the action prediction module is still not robust, in a sense that it's not able to have a very tight bounding of this specific audiovisual event when things are happening. So this is up till stage 2, and this is up till stage 3 when policy and the distillation module is jointly trained together. We see more stronger temporal grounding, and also cases of detection which are very much robust. Similarly, for another sample, we see similar results. So here we see that 1760 is the frame number where the next event has already started, but it is still detecting the take tablecloth action, doing the detection as the previous task, which is a case where there is a fault in the model, but then of course it has been rectified after the stage 3 training and fine tuning, which is definitely improving. A quick look at the active speaker localization task. So this was realized on Meta ARIA glass. We have 6 different audio channels, but in most cases we worked on 4 audio channels because the other 2 were not giving us a lot of gains. It was like very delta improvement over 4 from between 4 to 6. So this represents the position of where the different microphones are, and then red and the green blocks represent which channels are being activated and which are not being used at a specific instance. So in most cases we see that using EgoAdapt we are able to detect the correct and more optimized channels which are essentially required. So if the speaker is towards my right, we are targeting to activate the channels which are to my like towards the right part of the the glass, and so on and so forth, and the others are selectively being turned off, which is making sure that the overall compute and the channel usage for the audio is optimized. Now, what are some of the what are some of the efficiency results if we compare EgoAdapt with some of the standard, very well performing action recognition models? For example, TIM, which is of course our teacher model, and then AdaFuse, Ego only, STSS, listen to look, all of these models, we are seeing that it's order and magnitude smaller. And also, if we look at the top one accuracy, it's almost at the same level. Similarly, for active speaker localization, we are seeing significant gains. This is the on-device realization result, where we are using different quantization techniques, 4, 8, 16, 32, so on and so forth. We eventually go with the 32-bit model, but also even if we compare with the other like quantization, there are almost similar performance, but the overall energy consumption is a bit like over the boundary. But then that's up to us, like which one do we want to optimize to what extent. And this is the SNR versus use of video modality. We see optimally around 60% of the cases where the video modalities are selectively used, which is essentially giving us the highest performance in the like MAP for the action recognition task. So the overall takeaway, Gmax are reduced by almost 89%, parameters are reduced by almost 82%, and then energy consumption is reduced by almost 9.6 times. So if you have any questions, I'll be happy to take, and otherwise look forward to the poster session on 22nd. Thank you.
All right, I think we out of time for questions. So if you have any questions offline,
yes,
Sanjoy, please question or the host.